Imagine a future where global mobile data traffic increases exponentially, reaching new heights by the end of 2022. As we stand on the cusp of commercializing 5G systems, the thirst for innovative technological advancements becomes more pronounced than ever. The world is not just moving, it's sprinting towards a new era, an era of next-generation networks. These networks are not mere upgrades of their predecessors. They are envisioned to be the lifeblood of a dynamic and diverse range of applications and scenarios. From virtual reality to 3D printing, from self-driven cars to cyber-physical systems for intelligent transportation, these networks promise to be the backbone of a digitally transformed world. But as we look towards this promising future, it's essential to remember that the success of these networks will hinge on their bandwidth, transmission and processing delay, and efficiency. As we move forward, the capabilities of these networks will be defined by bandwidth, transmission and processing delay, and efficiency. But what happens when we reach the limit of these capabilities? The 5G systems, despite their game-changing design principles, have their limitations. Just like every other technological advancement, 5G is not without its flaws. Let's delve deeper into this. One of the primary limitations of 5G lies in its available bandwidth. Although 5G has significantly more bandwidth than its predecessors, it still isn't enough to support the exponential increase in global mobile data traffic we're expecting in the coming years. By the end of the year 2022, we're looking at an over 10-fold increase, from 7.2 to 77.5 exabytes per month. That's a lot of data, and 5G might not be able to keep up. Transmission and processing delay is another challenge for 5G systems. In a world where we're looking forward to virtual reality, 3D printing, self-driven cars, and more, zero response time is a necessity. Unfortunately, 5G can't quite deliver on that front. There's still a noticeable delay, which might not seem like much, but can be the difference between a seamless virtual reality experience and a dizzying one. Spectral and energy efficiency are also important factors to consider. While 5G does offer improvements in these areas compared to 4G, it's still not as efficient as we'd like it to be. Energy consumption is a significant concern in our increasingly eco-conscious world, and 5G's energy requirements might not be sustainable in the long run. These limitations of 5G have led to the need for beyond 5G or B5G networks. These next-generation networks are envisioned to support a diverse range of novel applications that demand high data rates, agility, flexibility, and reliability. But to do so, they need to overcome the limitations of 5G. To overcome these limitations, networks B5G need to focus on the vast, unutilized, and largely unallocated higher frequency resources in the optical band. By tapping into these resources, B5G networks could potentially offer connectivity speeds up to 1 terabit per second, opening the door to a whole new world of possibilities. But that's a story for another time. For now, let's just say that the future of wireless technology is looking brighter than ever. The future of wireless technology lies in beyond 5G networks. As we journey into the realm of beyond 5G or B5G networks, we're looking at a paradigm shift that promises to change the way we interact with the world. This leap forward is set to transcend the limitations of 5G systems, marking a new dawn in wireless communication. One of the most potent tools in the B5G arsenal is the optical wireless link. These are channels that tap into the vast, largely unallocated higher frequency resources in the optical band. Imagine more than 500 gigahertz of continuous and exploitable bandwidth lying dormant, ready to be harnessed. This untapped resource could lead us to a world of 1 terabit per second connectivity, combining large available bandwidth with spectral efficient transmission and access schemes. However, every technological advancement comes with its set of challenges. Optical wireless links are no exception. They suffer from severe path and penetration losses, which means they have low transmission range and are susceptible to blockage. The main culprits? Interactions and energy absorption by the molecules, mostly water, in the propagation medium in this band. So, how do we navigate these obstacles? The answer lies in innovative solutions such as high-direction connectivity, coordinated multipoint, relaying, and optical reconfigurable intelligent surface-aided approaches. High-direction connectivity, employed in both the transmitter and receiver side, can enable a connectivity range of several tens of meters and support mesh topologies. This also allows the utilization of space division multiple access, supporting a massive number of connected devices. Coordinated multipoint, relaying and optical reconfigurable intelligent surface-aided approaches also hold immense potential for expanding range and dealing with blockage. These solutions, when combined, could pave the way for a more efficient, agile, and robust B5G network. In the grand scheme of things, these advancements are paving the way for a future where networks can inherently support a huge dynamic and diverse range of novel usage scenarios and applications. Beyond 5G networks promise to revolutionize the way we connect and interact with the world around us. And at the heart of this revolution lies the development of MINOAS. As we navigate the uncharted territories of beyond 5G networks, MINOAS emerges as a beacon of innovation. This machine learning-aided optical wireless network is poised to become the backbone of next-generation technology, bringing us closer to a future where the limitations of bandwidth and transmission delays are things of the past. The potential of MINOAS is vast. It's designed to support a massive number of connected devices, opening up possibilities for a world where everything from your toaster to your car is interconnected and operating at peak efficiency. But it's not just about quantity. MINOAS brings quality to the table as well. One of the standout features of MINOAS is its inherent physical layer security. Thanks to the solitary line of sight links it establishes, data transmissions are less susceptible to interference or interception. This means that not only can we connect more devices, but we can do so with the confidence that our data is secure. But as with any groundbreaking technology, there are challenges to overcome. One of the key issues faced in the deployment of MINOAS is the design of innovative, low-latency device discovery and beam tracking for moving and mobile nodes. As our world becomes increasingly mobile, the ability to maintain stable and efficient connections on the move is paramount. This is where machine learning comes into play. By leveraging the power of artificial intelligence, MINOAS is able to adapt and respond to the ever-changing conditions of the network. It's a bit like having a constant tune-up for your wireless connection, ensuring that it's always running at optimal performance. So what does the future look like with MINOAS? It's a world where connectivity is no longer a luxury, but a given. A world where data flows freely, securely, and efficiently. A world where the boundaries of wireless technology are constantly being pushed and reshaped. Stay tuned for more updates on the exciting development of MINOAS as we continue to push the boundaries of wireless technology.